Alright, so now the next topic that we are doing is shallow foundation, right? And shallow foundation, we are going to discuss what are different types of foundations, okay, and how do we primarily design these foundation. Designs, in a sense, we're not going into the RCC and the steel details, but how do we arrive at the dimensions of these foundations based on the settlement criteria. Okay, in this particular chapter, the main emphasis will be on settlement criteria. However, that is not the only criteria which decides or determines the size or the type of foundation. There is also shear criteria. Shear criteria we will handle later. Initially, we are only starting with the uh, design or planning of the foundation based on the settlement criteria. Now, why do we provide foundations? So let's go start from the fundamentals. First is distributing the for a large area. Then, of course, to prevent differential settlements, to provide a level surface for the structure, to prevent undermining. Okay, then we provide the foundations are also provided in order to give stability against sliding and overturning, and to minimize distress against soil movements. Okay. So now, primarily, foundations are going to be divided into two categories. One is shallow foundation, and the other is foundation. Okay. And in shallow foundations, we have isolated footings, right? We have combined footings, we have strap footings, mat and raft foundation, mat or raft foundation. Also, in deep foundations, we have tiles, cofferdams, and casings. So starting with shallow foundation, the first one is isolated footings. Okay, they're also called pad footings. Okay, now if you look at the image, what are these? These here you can see a rectangular footing. So you see the first one is a rectangular footing. I hope the cursor is visible. Then we have a step footing. Okay. Then we have a trapezoidal footing. The most common ones being these slope footings or trapezoidal footings. Okay. Now, if you have a load-bearing wall, okay, that wall will have a foundation like this. It's a step foundation. So this in this image, they've shown how a foundation is provided for a wall. Now, in such cases, when you have these kind of rigid foundations, how is the pressure distribution? If you look at the pressure distribution diagrams, the diagram A, B, and C, they're different type of diagrams. Now, how is that exactly same type of foundation is having a different type of pressure distribution? Now, what do you understand by pressure distribution? Pressure distribution is the reaction of the soil beneath the footing. Now, as the soil type changes, then this reaction is also going to change. The first, the diagram A is fundamentally for cohesionless soil. So this is basically for sands. This is for sands. This is for clays. What is this? I'll tell you later. Now, actually, theoretically, for sands, the pressure distribution goes like this. It's basically near zero, theoretically. Yeah? Theoretically, it is near zero, okay, at the edges and maximum at the center. Similarly, for clays also, as you approach the inner part of the trapezoidal footing or any type of spread footing, the it's exactly ulta, you can see, exactly opposite of what you see in case of sands. But practically, when we are designing or we are planning any kind of structure foundation, we consider the pressure distribution like this. So from practical aspects, we consider it to be rectangular. So basically, we are being over safe. If we are dealing with sands, we are over safe at the edges because actually pressure, contact pressure at the edges is zero. If you look at this, it is maximum. Nearly you can say same as what is there at the center. And if we are dealing with clays, then we are being over safe at the center. So actually for clays at the center it is way less, but we are considering more. So this is actually oversafe thing. Okay, so you could just take down these figures if you write over the next slide. Now, the next type of foundation is combined footing. Now, what is a combined footing? Let's say the columns are coming very close to each other and it is not possible to provide a separate footing for each of the column, or the footing areas are such that they are overlapping, then you go for a combined footing. Now, this is useful in two ways. First and foremost, you are not going to invest in huge foundations. Okay? For each column, the area which is supported is becoming bigger. So this becomes more economical than providing two separate footings for these columns. The pressure distribution in case of combined footing. Now, if you look at this particular figure, look at only the top plan, right? Now, this column is bigger, this column is smaller. When do we provide bigger columns? It's obviously when the loads coming are heavier. When do we provide smaller columns? When the loads are lesser. So this is, you can see, it is corresponding to the contact pressure distribution. Heavier the load, higher will be the contact pressure distribution. Correct? So you can see at this point it will be lower, at this point it will be higher. I will not go into the details as this is just a fundamental class. Eventually, when we are dealing with the planning and design of each and every foundation, we will go into details of this right? Then the next is strapping footing. Now, what is a strapping? You can see in the image, it's not very clear, but still it's easy to understand. This strap is flushed with the top surface of this pad footing. Yeah, the top of this strap is nothing but a beam which is connecting two columns. Now, if you can see, this is an eccentrically loaded column. Now, when do you provide an eccentric column? A classic example would be you have a plot and you need to provide column at the plot boundary. Correct? Now, let's say this is your plot boundary. Now, you cannot provide a regular foundation because then in that case, to provide the foundation, you have to dig inside the neighbor's plot. So, what is usually done? You provide a eccentric footing. Now, if this is going to be eccentric, it is safer to tie this particular footing with a footing which is closest to it. So how do you do it? You do it by providing a strap. Now the strap is nothing but RCC beam which connects these two footings, these foundations. Now usually this strap is kept disconnected from the ground level. So if I try to show you in plan and then erection, you can see the strap. Now this will be your soil will be everywhere here. So strap is little bit above, so it's not actually getting connected, it's not in contact with the soil. That's the reason you will not find any contact pressure distribution for the strap. You will see the contact pressure distribution for these two footings, just like how we saw before. This is the contact pressure distribution diagram for a strapping footing. Then the other type of shallow foundations that we have are grillage foundations, wherein you have a network of I sections or other built-up sections of steel. Okay, and then the next one is mat. Now, mat or a raft foundation comes under shallow foundation. The reason being the fundamental thumb rule for while defining a shallow foundation is that the width of the foundation has to be larger than the depth. Now, obviously, mat foundations they are huge foundations, so they will definitely be under the shallow foundation category. Now, next subtopic is safe bearing pressure. Now, these are some equations which are given for safe bearing pressure. I have started this particular topic before I cover the bearing capacity topic. Ideally, it would have been better if I had to cover bearing capacity before I started with shallow foundation. Nevertheless, I will try to cover all the concepts which are required for this particular chapter and whatever are the prerequisites from bearing capacity chapter. I have embedded the videos which are covering those topics. So, what you could do is you could pause and go through the video which is provided in the description. Okay, watch that video. Now, when you determine safe bearing pressure or safe bearing, it's fundamentally based on two criteria. One is shear and other is settlement. And in this chapter, we are concentrating on this particular criteria. So, the equation for allowable bearing, okay, for various types of foundation, strip foundation, square. So, where do you see strip footing? I had shown you something like a wall foundation, okay, or a square footing, or a circular footing, and a rectangular footing. They have different equations. Now, I will concentrate on just one particular equation and explain all these terms. Okay, so QS stands for the safe bearing capacity. Okay, and F is your factor of safety, which goes from 3. Now, mind you, we are finding out the safe bearing capacity or safe bearing pressure from settlement criteria. Let's say you get safe bearing pressure from settlement criteria as, let's say, 15 tons per meter square, and from shear criteria you get it as 12 tons per meter square. Then, while designing the footing, you are going to take the lower one to be safe, because if you take 15, then your foundation will be safe from settlement criteria, but it will fail in shear. So you always take the safe bearing pressure, bearing capacity, um, out of the two, whichever is yielding you the lower value, that is taken for your design, obviously to be on a safer side. So now in these equation, what are all these different parameters? F stands for factor of safety, which goes from 2 to 3, and it can go even higher if the structure you are dealing with is very important. Okay, so and then C is for cohesion. NC is a bearing capacity factor. Okay, we will be dealing more about this. How do you get this NC, and all you need to understand that these factors we obtain from the IS codes. They are mentioned in the IS codes, and there are multiple theories which are used to determine this particular factor. Okay, so NC is the bearing capacity factor related to cohesion, NQ is the bearing capacity factor related to friction, and N gamma is the bearing capacity factor related to unit weight. Okay, gamma is unit weight, D is the depth of the foundation, RW are the water reduction factors. That is basically how will your water table or presence of water affect your bearing capacity. That is taken care by this factor RW. RW1 and RW2 both are water reduction factors. Okay, so these are the equations for safe bearing pressure, safe bearing capacity for various foundations, and the theory that is used for arriving at these particular equations is Terzaghi's theory. And okay, B is the width of foundation. These are the values. Now, NC, NQ, and gamma, if I'm using them in my equations, then the type of failure expected in the soil is general shear failure. And if I'm expecting local shear failure, then the factors are NC dash, NQ dash, and N gamma dash. All these factors are available in your IS codes. Okay. Now, what is general shear failure and what is local shear failure? I have explained in my video which is embedded in the description. Please make sure that you watch this video before you continue further. Pause this video over here, watch the video on modes of failure in case of foundation, and then we will